To illustrate the variational method, let's consider a special example. In this example, I want to use a trial function, which I will say is a function of r, and it's parameterized by a parameter alpha. And this function that we'll try is a Gaussian function that looks like this. Now we're going to apply this to the hydrogen atom, and we know that this is not a solution to the hydrogen atom, so this will give us a way to see how the variational principle works when we apply it to a real problem. Now the Hamiltonian for the hydrogen atom is given up here. I've rewritten it again over here to the right in terms of a Laplacian term that is dependent only on the r variable and the angular momentum result. And of course we have the Coulomb term here at the end, which is the potential for the hydrogen atom. I'll remind you that the radial part of the Laplacian is given over here. And we're going to do this for a specific case where the angular momentum is equal to 0, so that is we can eliminate that term. We can just forget about it. Now when we go to apply the variational method to this problem, we're going to need to calculate the expectation value of the energy, okay, which is for this particular trial function, and in general it will be a function of the parameter alpha. Now the way we would normally write this down is we would find the expectation value of the Hamiltonian divided by the square of the wave function below it. And I'll just remind you that this is equivalent to an integral dr r squared. We'll have the trial wave function, the Hamiltonian operator, the trial wave function, and this is divided by the integral 0 to infinity dr r squared and just the product of the wave function with its complex conjugate. Now there's a shortcut I've taken here, and I hope you're mentally aware of this, mentally taking note of this. The hydrogen atom is actually a three-dimensional problem, and we have basically gotten rid of the two angular variables by setting L equal to 0 over here. So when we do this overlap the integrals, technically we have to include those angular variables also. But when we're in a system that is spherically symmetric, the result of those integrals is just going to be 4 pi, but we're going to get it both in the numerator and the denominator, so in fact we don't really have to worry about it too much. We only have to worry about the radial part. But I want you to be aware of this because you have to think of it. Think about the problem you're dealing with. This is a three-dimensional problem. It needs 3 coordinates to be integrated over. We have basically taken a shortcut to evaluate 2 of them in a very automatic fashion. Now, when we go to evaluate these integrals, the first thing we need to do is find out what is the operation of the Hamiltonian on this trial wave function. So let's figure that out. What we're doing is essentially this operation, where we're operating the Hamiltonian on this operator, which means that we're doing this series of derivatives in the radial coordinate, operating on e to the minus alpha r squared, and then we're subtracting the term that comes from the Coulomb potential. Okay, when I go through and evaluate this set of operations, derivative, multiply by r squared, take the derivative, divide by r squared, I'm going to get a term that looks like this. It'll be negative 2 alpha squared r squared plus 3 alpha, and then we'll have minus 1 over r, all of these things times our Gaussian function. So this is the result of operating the Hamiltonian on this Gaussian function that we're using as a trial function. But this implies 3 different integrals that I'm going to have to evaluate in order to get this quantity up here. Now all of these integrals are Gaussian integrals, so I've provided here typical Gaussian integrals, in fact exactly the Gaussian integrals that we need just to save a little time in the video, but these are Gaussian integrals that you can actually evaluate yourself without too much difficulty, or look them up in an integrals table, or do them with Mathematica or some mathematical manipulation software. So let's do them one at a time. So the first thing I have is minus 2 alpha squared times the integral 0 to infinity dr r squared, which is the volume element, and then I'm going to have another factor of r squared from the term, and then I have this Gaussian times the Gaussian represented by psi star, so I'll have minus 2 alpha r squared. Okay, so this is just r to the fourth e to the minus alpha r squared, so that's this integral right here. So I can immediately write down this is minus 2 alpha squared times 3 over 32 alpha squared times the square root of pi over 2 alpha. And if I figure all this out, it's minus 3/16 square root of pi over 2 alpha. All right, for the second term, I'll have 3 alpha times the integral dr r squared, which is the volume element, and then I don't have any terms that involve r over here, so I'll just have e to the minus 2 alpha r squared. This turns out to be the second integral I've got here, so I'll have 3 alpha times 1 over 8 alpha square root of pi over 2 alpha, and when I figure all that out, I'll end up with 3/8 square root of pi over 2 alpha. Now you notice when I add these two terms together, 3/8 minus 3/16, that's just 3/16, so the sum is just going to be 3/16 times the square root of pi over 2 alpha. And it's positive because this term is positive and that one's negative. All right, lastly, I'm going to have the Coulomb term, which is minus 1 over r squared, so I'll have a minus integral dr r squared 1 over r e to the minus alpha r squared, 2 alpha r squared rather. The 1 over r and the r squared combine to make an r, which is this integral up here, so this will just be equal to minus 1 over 4 alpha. So now what this tells me is that, I've got one more integral to do. I've got to do the integral down here in the denominator. So let's do that one. So I'll have integral, and I'll have dr r squared e to the minus 2 alpha r squared. Well, that's just the same integral that I had to evaluate up here. I don't have the factor of 3 alpha multiplying it, so I will simply have 1 over 8 alpha square root of pi over 2 alpha. So now when I evaluate the expectation value of the energy, this term here, I will end up with the following. I'll have the sum of those two terms minus 1 over 4 alpha. So that's the Hamiltonian term in the numerator, divided by 1 over 8 alpha square root of pi over 2 alpha. All right, so we're going to turn this upside down. So this thing inverted will give us 8 alpha square root of 2 alpha over pi. So that's what I need to multiply by each of the terms here. So I'll have 3/16 square root of pi over 2 alpha times 8 alpha square root of 2 alpha over pi. Okay, well, the square root of 2 alpha over pi terms are going to cancel, and I'll just have 8 alpha divided by 16 times 3, which will be 3/2 alpha. Okay, for the other term, minus 1 over 4 alpha, multiplying by this same set of constants, I'll get that. So this first term, 3 alpha over 2, as I indicated, okay, because the 8 will cancel with the 16 to give 2, and I'll have a factor of alpha in the front. Then minus 1 over 4 alpha, 8 alpha, that just gives a factor of 2, so I'll have minus 2 times the square root of 2 alpha over pi. So I can rewrite this as 3 alpha over 2 minus the square root of 8 alpha over pi. And so this is my result. But is it my final result? Well, remember in the variational principle, we have to find the value of alpha that optimizes, that minimizes the energy. So what we're going to do is go to the next page. I'll repeat this result that we got. 3 alpha over 2 minus the square root of 8 alpha over pi. And now what we need to do is we need to take the derivative of this with respect to alpha, set it equal to 0. So we're going to find the optimal value of alpha. Okay, when we do this, we'll get 3/2 minus This is alpha to the 1/2. Derivative of that is going to be 1/2 alpha to the minus 1/2. So the net result of that is 8 over pi alpha. Okay, the 8 and this will cancel, so I'll have 3/2 square, minus 2 times the square root of 2 over 2 times the square root of pi alpha. So we'll have 3/2 minus the square root of 2 over pi alpha. All right, so now we need to solve for alpha. So when I square both sides, so when I set this equal to 0 and square both sides, I'll have 9/4 is equal to 2 over pi alpha. If I rearrange this to solve for alpha, I'll end up with alpha is equal to 8 over 9 pi. All right, so this is the value of alpha that optimizes our arrangement. When we plug this into our expression for e to the e sub phi of alpha, we will end up with the following. We'll have 3 over 2 times 8 over 9 pi minus the square root of 8 over pi times alpha, which is 8 over 9 pi. And conveniently, this will all come out of the square root eventually. So we'll have 24 over 18, or 4 over 3 pi, like that, minus, I'll have 8 squared, so that's 8, pi squared, which is pi, and 9 squared, 9 is 3 squared, so 3 pi. So I'll have 4 over 3 pi minus 8 over 3 pi, so negative 4 over 3 pi is the final result. Now remember, this is in atomic units. So what this tells us is that our variationally optimized result in atomic units is minus 4 over 3 pi, which is negative 0.424. Now for the hydrogen atom, the actual, and I shouldn't say E0, it's E1, the actual ground state is minus 1/2, or minus 0.5. So you can see that the variational result is not the same as the actual result, but it's within the ballpark. It's off by a few percent. This has not been an especially good variational wave function to use for this, and one can devise much better ones. But we do get a sense for how one applies the variational principle to find a upper bound to the ground state energy, in this case the hydrogen atom, that is indeed above the energy of the hydrogen atom, and how this in effect works when we have a parameterized trial wave function.